Welcome to the video podcast regarding specific and latent heat calculations. Calculations of specific and latent heat problems have a lot of exotic symbols, and we really need to clarify what these symbols mean and to incorporate that in our thinking and in our data tables so that we remain well organized. In these problems, a lowercase q will represent the energy quantity in either joules or calories. C subscript P will represent the specific heat of a substance, and the specific heat of a substance is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. The units for this are joules per gram times degree Celsius or calories per gram times degree Celsius. For our portion here at Ontario High School, we will use joules because this is the SI unit. Calories is more of an older unit, and it's useful in some ways, but we prefer joules. So again, this C subscript P is a unit that we will use consistently through the class. You may see it sometimes in other settings such as textbooks or online. You may see it as just represented by a C, or you may see it represented by SH. But for our purposes, C subscript P. Continuing with our symbols and abbreviations, a lowercase m will represent the mass of the substance in grams. Capital T will represent the temperature in degrees Celsius. Kelvin can also be used for this, but generally we'll use degrees Celsius. The symbol H with FUS subscript represents the latent heat of fusion, which is represented in joules per gram or sometimes in kilojoules per mole. The H VAP subscript is the latent heat of vaporization, also measured in joules per gram or kilojoules per mole. Some important keys to understanding these type of problems is that specific heat values are used when a substance is changing temperature due to heat being added or removed. Latent heat values are specific to phase changes, and these phase changes include melting, freezing, boiling, and condensing. We are going to be analyzing and solving some problems having to do with the transfer and storage of heat, and in order to do this, there's a lot of information that we will acquire by comparing experimental values or values in our problems to known things that we know about water. Okay, so this would be a great time for you to pause the podcast and write down these known values, both on this slide and the next slide, because they'll be used quite frequently when we do our problems together. So specific heat values for water depend on the phase. So in solid ice, the specific heat is 2.050 joules per gram times degree Celsius. For liquid water, it's 4.184 joules per gram times degree Celsius. And finally, for water as a gas or steam, it's 2.080 joules per gram times degree Celsius. When you look at these values, it tells us that liquid water requires much more heat, twice as much heat in fact as ice, to change its temperature. And the same with steam, that liquid water takes twice as much heat added or removed to change its temperature by 1 degree. A couple other of the known constants for water that are very useful to us are the latent heat values. The latent heat of fusion, or delta H FUS, is 334 joules per gram, or 6.012 kilojoules per mole. The latent heat of vaporization is 2260 joules per gram, or 40.68 kilojoules per mole. These specific and latent heat values are unique to water. These are characteristic or intrinsic properties of the substance. This means that each substance that we will examine has a unique, specific, and latent heat value associated with it. This can actually be used to identify substances. This may be a good time for you to pause the podcast and write down some of the equations that I'm going to share with you. These are equations that deal with specific heat problems. We have Q, which is heat in joules, is equal to the mass of the substance times the specific heat of the substance times the change in temperature. That delta sign in front of the T means change. We can rearrange this equation to solve for specific heat by making that equal to the heat in joules, Q, divided by the product of the mass times the change in temperature. And we find the change in temperature, delta T, by taking the final temperature minus the initial temperature. It's very important when you do that you include the sign. Sometimes that change in temperature, if heat is being removed from a substance, that change in temperature will be negative. Remember that specific heat has to do with change in temperature, how much heat needs to be added or removed in order to change the temperature of 1 gram of a substance by 1 degree Celsius. These equations that you're looking at right now have to do with latent heat. And we said earlier that latent heat does not have to do with the change in temperature of a substance, but it has to do with a change in phase, either melting, going from a solid to a liquid, or freezing, going from a liquid to a solid, or boiling, going from a liquid to a gas, also called vaporization, or condensation, which is going from a gaseous state or vapor state to a liquid. So if you would write these equations down as well, pause the podcast if needed. But we can calculate heat, which is Q, represented by Q in joules, is equal to the product of the mass times the latent heat of fusion in the case of a phase change involving a solid and a liquid. And if the phase change involves a liquid and gas, then Q in joules would be equal to the product of the mass times the latent heat of vaporization. Let's try a sample problem together. How much heat must be added to 50 grams of a sample of water to raise its temperature from 20 degrees Celsius to 50 degrees Celsius? Whenever you're solving problems dealing with specific or latent heat, and what really would be a good idea with any type of quantitative problem solving in chemistry or physics is that you write a data table first. So in my data table, I have the variables set up from the relationships between heat, represented by Q, mass, which is represented by M, specific heat, which is C subscript P, and delta T, which is the change in temperature. I know that because this is liquid water, it's not being frozen or boiled, and that there is a temperature change, that I'm going to use the equation that involves specific heat and temperature rather than a latent heat equation. So Q is what I'm trying to find, so I put a question mark there. My mass is 50 grams of water. The specific heat of water, liquid water, is always 4.184 joules per gram times degrees Celsius. And finally, my change in temperature is the final temperature of 50 degrees Celsius minus 20 degrees Celsius, which gives us a change in temperature of 30 degrees Celsius. Once I have my data table, I want to look at the equation for specific heat and arrange that equation so that it solves for the unknown. Now, in this case, Q is already isolated because our base equation is Q is equal to M times C subscript P times delta T, which is the mass, times the specific heat, times the change in temperature. So all I need to do now is, in my working equation, replace these symbols with the actual values. So we have 50 grams times 4.184 joules per gram times degrees Celsius times 30 degrees Celsius. The answer to this is 6,276 joules. Now, because my mass is 50.0 grams, there are 3 significant figures with that number, and my temperatures are also expressed in 3 significant figures. The specific heat value is a known value, so it does not affect the number of significant figures. So I need to adjust my answer to reflect that 3 is the maximum number of significant figures I can show here. So my answer for the amount of heat that must be added to a 50 gram sample of water to raise its temperature from 20 degrees to 50 degrees Celsius is Q is equal to 6,280 joules. Let's try another problem. Here we want to know how much heat must be removed from a 25-gram sample of iron to lower its temperature from 200 degrees Celsius to 25 degrees Celsius. So we set up our data table. We're trying to find Q, so we put a question mark there. Our mass is 25 grams. The specific heat of iron is 0.450 joules per gram times degrees Celsius. If you notice, iron has 1/10 the specific heat that water does. So again, this is a characteristic or intrinsic property unique to the substance. Our change in temperature is our temperature final, which is 25 degrees Celsius, minus our initial temperature, which is 200 degrees Celsius. So our change in temperature is a minus 175 degrees Celsius. Our base equation here, Q is equal to M times C subscript P times delta T, is also our working equation because we're trying to solve for heat. So we take our mass of iron, 25 grams, multiply it times the specific heat of iron, 0.450 joules per gram times degrees Celsius, and multiply that times the change in temperature, which is negative 175 degrees Celsius. We have an answer of 1968.75 joules with a negative sign in front of it because the iron is cooling, heat's being removed from it. And you can think of this in this way, if it helps, in that when something is getting cooler, it is subtracting heat out, and so the Q value must have a negative sign in front of it to reflect that. When something is getting warmer and the temperature is rising, then heat being added, we use a positive sign with that. Although with heat being subtracted or heat being lost, in this sense, or being removed, the negative sign is necessary. The positive sign is implied if it's not there. If you do not see a negative sign, then the heat is being added in its positive value. So we want to adjust this to the correct number of significant digits, and there are 3. So Q would be equal to negative 1970 joules. And again, please note, heat added is positive, heat removed is negative. This is the end of part 1 of the latent and specific heat series, video podcast here at Ontario High School. So hang on, part 2 is coming, and very important that you continue through these sample problems and figure out how to do these. Please enjoy this quote by Mother Teresa.